it's more like a chance, an opportunity that I can put some concept that I have into words, right? And I can build a team. And my day job is trying to understand how quantum computing works and how quantum computing can create values to humanity. And in the meantime, I'm interested in consciousness, and I want to try to understand how these two things link together. I have some ideas, but ions give me a reason to put this into text, right? So without further ado, let's move into my topic today. So first of all, this reward is about creating a conscious AI, and I would like to start to thinking about it, like what that even mean. Like for our audience, this I understand this is our third presentation today. You might be tired, so let's make some brain teasers about thinking about like your favorite AI tool here, for example, like ChatGPT. And do you believe that this thing have a consciousness at all? And most likely you would not believe that because otherwise you won't be here and you are satisfied. We already built a conscious AI. But the deeper question is that why not, right? Why do you not believe in that? Is that just because are some human arrogancies that believe that it's just functional thing, right? To me, this question seems to be a hard question. So my way to do that is trying to make it simpler, right? And again, just like a quick thing for the third presentation. Here I will list some systems, and if you feel that any of these systems are consciousness, if you can make some reactions with a reaction button, that would be great. First of all, it's just a for me, it's just the simplest thing I can imagine. It's like a rock, or it's like something that's very stationary, very predictable, and it doesn't move. And I know almost everything about it. At least seems like so. If you believe this a rock have consciousness, please, just make some reaction. And the third one and second one I want to mention is like a coin that you are flipping, right? You flip a coin and you close it. You don't know what it is. You don't know the answer. And you can make a prediction saying that, okay, it's a 50-50 chance. You get a head or you get a tail. However, you have to understand also that this flip coin is not decided by itself, right? It's like, okay, it's predefined. It's if we know everything about, for example, like how hard you flip the coin, what's the air resistance there, like what's the surface bounce, how it will bounce on the surface, you might be able to predict the result of this coin. And the third one is kind of like a coin, but you don't know. Like no matter how hard you are trying to understand the initial conditions, the environment it is, no matter how hard you are doing that, you can only use a prediction. You can only say that, okay, there is a probability that is like 50% of chances ahead. Like even if you know everything about this coin. So I guess what I'm trying to say here is that if you want me to believe that a system somehow possess consciousness, there must be some room for my interpretations saying that there is a chance that this system could choose its own state no matter how hard we probe it, no matter how hard I'm trying to understand it, no matter how hard I'm trying to use a theory to predict the result of it, there's still a chance. There's still a possibility that this system seems to be on its own. Well, luckily, we do have this perfect coin in our nature, and well, not allowed by Newtonian mechanics, but allowed by quantum mechanics. There are two things I would like to mention. I don't have the time to get into too much details, but here I'm listing some links for a basic explanation of both. Number one is Bell test or Bell theorem. Basically, what it's saying is a quantum system doesn't have hidden variables. That okay, even this hidden variable doesn't exist to predefine its result that you are going to observe. Number two is by Conway and Cauchy, um, free will theorem. Basically, what it's saying is that if we believe, well, of course, under some assumptions of axioms, that sounds very plausible. If we believe that a human could possess some sort of free will, so basically, it means that our action later will not be a function of our history or environment, or at least not only a function of the history of the environment. So does some element particles and like protons, electrons. And when we are observing these particles, they kind of choose their state by themselves. In the meantime, we human beings are also trying to build a system that harness these sort of element particles. We call this in a way of qubits as a mathematical object of these element particles. There's various modalities we are trying today, and we call those devices in general as quantum computers. Um, these computers are noisy. It's not as perfect as we imagine to be built, but however, it seems to be able to serve at least some purpose, as Conway and Cauchy mentioned as free will theorem. And in the meantime, these quantum computers could do some certain type of computations better than our classical ones, and that's why people are trying so hard to build it. But here I'm trying to mention that it's not like almighty machine that you can do all your computation from them. So, well, for the scope of this award, it seems like our question seems to be solved, right? So the only thing something we can do is just somehow glue some sort of quantumness to our AI system, and we can call such a thing conscious. However, here we're trying to say is that yes, building a system and you call it conscious is an easy task. But to my opinion, we take it into a practical angle saying that, okay, if you claim that your conscious AI is better, you have to somehow outperform today's AI that you believe is not conscious, at least in some specific tasks. And that brings us to the question is saying that, okay, what are these tasks? Like, what are these tasks that our today's quantum computer can do better comparing to our classical systems? And unfortunately, there's only very a handful of choices. But one of these choices is what we called quantum sampling. So sampling is basically means that just like you're throwing coin and you know in the future that okay, in the future it will be like 50-50, and you actually flip the coin and get your answer, and you flip it thousands 10,000 of times, and you get a bit string of your result, and this process of flipping the coin is called sampling. And no matter how hard you are well, but okay, what I'm trying to say here is that for like the easiest case scenario, like a coin, this seems to be an easy task, even for a classic computer to do. However, you can also imagine that your probability density distribution could be complex. Like in the term of there might be more than one coin, there might be those coins may be correlated somehow, and when this degree of freedom dimension getting larger and larger, you can also imagine that the distribution could getting more and more complicated. And this will be very hard for a classical computer to do because only thing it can do is just do a like a do a like a even distribution and skew that even distribution with your probability density functions. However, this could be a quantum easy task, and it seems to be a very short presentation to understand why this is quantum easy. But here I have like a one sentence hand wavy heuristics to help you understand. It's kind of just like the coin metaphor that I'm using earlier is that it seems like this quantum computer have some freedom to choose its own state. And that's why sampling is very easy. It's just a measurement in the quantum language. Now, why this is related to why we think that quantum sampling is a task that's related and can be used in today's LLM system or AI. And here we find a niche angle of this task that almost every language model is using today is called word embedding. So word embedding is like a process that maps your word to some data. And this data is basically a vector in a semantic space. And here, for example, like a man may be mapped to 1, 7 in this map, and some other words may map to somewhere else. And notice that here the semantic space seems to be have some meanings, but in reality, the semantic space doesn't really have that very specific meanings here. And what we are proposing here is that it doesn't seem to be a really good or very intuitive idea. It's more likely, at least what I'm thinking about how I process word. It feels like I'm not mapping a word to a specific meaning, but actually what I'm feeling is that I'm mapping a word to a distribution of meanings. That could be means a lot of things, but okay, there might be a mean value of this a lot of things, but as we can see, like some of the words have a bigger distributions, and some of the words may have very specific meanings. And that's what we're trying to say is that for a quantum version of word embedding, we can actually map this word onto a distribution. Or actually, every time I'm trying to draw a meaning of a word, we actually draw a sample from this distribution. So why this is good, right? Why we think that quantum word embedding is good? It seems like you are just adding. It seems like at the very first glance, we are just making things a little bit more complicated. It's why a distribution seems to be better than a point or than a vector. I think here are at least two reasons that we can think about it. Number one is that it seems to be more natural for us to comprehend some semantic relationship. At least two example here. And for example, like hypernym basically means that one word have a broader meaning comparing to another. Um, in word embedding, it's basically just 2 points, and you do some sort of rotations to make this relationship happens. However, this relationship is very hard. It's kind of unnatural for me, at least, to comprehend as a rotation in a semantic space. But here it seems to be more easier, right? It's for example here scarlet it have a like a narrower meaning comparing to the word red, and you just define a smaller space, define a smaller um, space in our semantic space for this word. Another one maybe is polymathy. Basically means that a word can mean two things or even more things. And for example, the word bank. And that's also easy for me to assign just two space in your semantic space for this word. The second reason is that not only you can interpret more meanings, but also you can change those meanings according to the context that you have. Like for example, here, if a bank is conditioned by the word river, you can assign, you can shrink the meanings that is close to a post office and making the meaning on the that close to the land a little bit bigger, or vice versa. If the bank is conditioned by the word of America, then you can do it in the opposite way. But more importantly, as I said before, I think the most important thing for me is that this representation of word meaning seems to be more like how I process word and how I assign meanings to when I heard one. So to close my presentation, I would like to thank our collaborators, Yidong, Jiaqi, and Anze. I would also like to thank the sponsors, including Ions. Here we also get some sponsorships from Amazon Bracket to make some preliminary experiments of our idea. And in the meantime, I would like to introduce our nonprofit, Thank You Tech Inc. So it's just like Ions. It's a nonprofit organization. Instead of working for Noetic Science, we focusing on quantum computing, and we would like more people. And no matter if you are quantum computing expert or not, there's always a place for you to learn more about it. And if you are interested to get involved in this particular work, feel free to send me an email, and there's my email. So I will just stop there and thanks the organization.